Hi everyone, welcome back. In this particular video, we're going to start talking about directing effects in electrophilic aromatic substitution reaction. This applies to aromatic compounds that are substituted. In a previous video, we have classified substituents on the aromatic groups as activating or deactivating. Activating groups on an aromatic ring are known to be ortho-para directing. What does that mean? That's what we're going to talk about in this video. So for the purposes of our discussion here, we're going to use two examples. The first example is the nitration of toluene. Toluene is an aromatic compound based on benzene and which contains the methyl group as a substituent. So if we do a nitration of toluene using nitric acid and sulfuric acid, we can expect three possible products here. We can get the orthonitrotoluene, metanitrotoluene, or the paranitrotoluene. Recognize that these different isomers are classified based on the proximity of the nitro group from the methyl group. So the substituent which was already there. So the nitro group, when it's on the second carbon, it's the ortho product. When the nitro group is on the third carbon relative to the substituent, then it is the meta product. And if the nitro group is on the fourth carbon relative to that substituent, then it is the para product. Now, also recognize that if we had the nitro group on the left-hand side here, that would still be an orthonitrotoluene. If we had the nitro group on the left-hand side here, it would still be metanitrotoluene. But there is only one possibility for the paranitrotoluene. So there's only one position which is para to that methyl group. Now, methyl group, as we know, is a weakly activating group because it is an alkyl group. And because of that, the reaction here, this nitration reaction, it occurs about 25 times faster than the nitration of benzene. What does that mean? That means if you were to run two reactions in parallel, one which is the nitration of benzene and the other one which is the nitration of toluene, the toluene nitration reaction is going to be going at a speed or a rate which is 25 times faster than the rate at which the nitration of benzene is going to proceed. So although there are three possible products that can form in this reaction, it turns out that all of them are not formed in the same amount or in the same ratio, which is expected. But it turns out there is a huge difference in what's formed. So when we look at the products from this reaction, we get this orthonitrotoluene product in about 63% yield, the paranitrotoluene product in about 34% yield, and the metanitrotoluene in about 3% yield. Again, these numbers, they do not have to be treated as absolute numbers. Essentially, what we are trying to say here is that we get about 60% of the orthonitrotoluene product, about 30% of the paranitrotoluene product, and very little of the metanitrotoluene product. Now, since we get the ortho and para products as major products here, we say that the alkyl group or the methyl group is ortho para directing. And what that means is we're trying to say that when an electrophilic aromatic substitution is going on in this molecule, this substituent, the methyl group, is somehow directing the incoming electrophile to the ortho or the para position, okay? So the substituent directs the incoming electrophile to the ortho and para positions. So that's why the methyl group is called an ortho-para directing group. In fact, what we're going to see later is that all activating groups are ortho-para directing. They all send the electrophile to the ortho or the para position, implying that those products are the major products in this reaction. To understand why that is the case, we'll have to look at the mechanism of this reaction. So to understand the origin of this ortho-para directing effect that we're seeing here, what we're going to do is we're going to examine the mechanism of this reaction. And we're going to examine the mechanism in detail with a focus on each of these products. How is each one of these products formed? So we're considering three scenarios here. We have the ortho attack, we have the meta attack, and then we have the para attack. So let's consider the ortho attack first. So if I start with toluene, and if we are considering the formation of the orthonitrotoluene product. Now recollect from an earlier video that when we do a nitration reaction, the electrophile that's formed under these conditions is a nitronium ion, NO2+. That's the electrophile in this under these conditions. So we're going to consider the nitronium ion here. So NO2+, that's our electrophile. And since we're focusing on the ortho product or the ortho attack, I'm going to choose one of the pi bonds which includes the ortho carbon. The ortho carbon should be involved in that pi bond. So it looks like I can use this pi bond because this is an ortho carbon, or I can use this pi bond because that's an ortho carbon too. Just for the sake of simplicity, I'm going to use this carbon here. That pi bond is going to go and attack the electrophile. So it attacks the nitronium ion. And this would now give us the sigma complex. So our sigma complex is going to have now a hydrogen and a nitronium ion over here, or the nitro group over there, sorry. And there should be a carbocation on the other carbon, the meta carbon, which was part of this double bond. That's going to now bear a carbocation or a positive charge on it. So we've made the sigma complex here. And as we know, the sigma complex is resonance stabilized. So we can draw various resonance forms for this sigma complex. So let's draw them out. So we can start with this pi bond, move it over because that pi bond, or because this carbocation is allylic in nature, we can push that pi bond over. So we'll get the methyl group here, H, and nitro group here. We have a double bond here, and now the carbocation has moved. We can draw additional resonance form using the other pi bond. So we've got double bond here, methyl group here, and a positive charge over there, hydrogen and nitro group. So those would be all the resonance forms for the orthonitro product. Now, from these resonance forms, essentially, any of these resonance forms can lead to the orthonitro product, because what has to happen is a weak base that's in the system, for example, water, it can come and deprotonate this hydrogen, and the electrons would fall into the space, and that would give us the orthonitro product. Methyl over there, and we've got the orthonitro product. So that's how the ortho nitro product is formed. Okay, I'm just trying to show you for the first example here. Now, so that's the mechanism for the formation of the ortho nitro product. Let's examine the mechanism for the formation of the meta nitro product. So if I start with toluene again, so for the meta nitro product, again, the electrophile is the nitronium ion. I'll have to choose a pi bond which includes the meta carbon or the meta position. And this pi bond that we used here was between the ortho and the meta carbons. So as the pi bond attacks this nitro group or the nitronium ion, it's going to give us a sigma complex. And this sigma complex would now have the nitro group on the meta position because we're considering the meta attack. So there we have it. And so the carbocation forms over there. There's a double bond here and there's a double bond here. This carbocation is resonance stabilized, or the sigma complex here is resonance stabilized. So we can draw various resonance forms for this. So we've got methyl group, double bond, H, NO2, double bond here, and positive charge. And we can draw further resonance involving the other pi bond. So we have double bond, methyl group, H, NO2, and we have a double bond here and a positive charge here. So those would be all the resonance forms for the meta product. And from this meta product, again, some weak base can come and deprotonate this hydrogen, which is going to drop its electrons into the ring, and it would give us the meta product. So let's say we are going to get the meta product over there. And we can do a similar mechanism for the formation of the para product. So for the para product, we start with toluene. We will use the nitronium ion as the electrophile, and we must use a pi bond which involves the para carbon. And the only pi bond that does so is this pi bond. So I'm going to use this pi bond to attack the nitronium ion. And very similar to the other cases here, this is going to give us a sigma complex where we now have the nitro group connected to the para carbon. We have a double bond here, and a methyl group here, and a positive charge here. And so that sigma complex is again resonance stabilized. So we can draw a few resonance forms for this sigma complex. We've got double bond here, H, NO2, methyl group, positive charge over there, and further resonance. Double bond, methyl group, H, NO2, and a positive charge over there. So those would be all the resonance forms for this sigma complex. And then as we've seen previously, any weak base can come and deprotonate this hydrogen, which is going to add electrons to the ring, and it would give us the para product. So we can make the ortho nitro product, the meta nitro product, or the para nitro product. So this would be the mechanism, or these are the mechanisms for the formation of each one of these products. And the fact that we get ortho and para products as major products and almost none of the meta product has to lie in the mechanism, the reason why that happens, okay, the reason why that happens. So now if we closely examine all the resonance forms for these sigma complexes, What we see is that in the resonance forms for the ortho attack, our carbocation is on a secondary carbon. It's on a secondary carbon, and then it is on a tertiary carbon. So one of the carbocations is tertiary in nature. If we examine the resonance forms for the formation of the meta product, we have a secondary carbocation, we have another secondary carbocation, and then we have yet another secondary carbocation. So it seems like all intermediates here are secondary in nature as far as the carbocation is concerned. Going to the para product, we notice secondary, tertiary, and secondary. So it seems like the difference between these various possibilities, ortho attack, meta attack, and para attack, is that in case of the ortho attack, which leads to the formation of the ortho product, and in case of the para attack, which leads to the formation of the para product, we have at least one resonance form here for the sigma complex. Okay, we have one resonance form for the sigma complex, which is more stable because of the tertiary nature of the carbocation intermediate that's formed here. As far as the meta product is concerned, or as far as the mechanism for the formation of the meta product is concerned, the carbocation remains secondary throughout all of these resonance forms. So the extra stabilization that this tertiary carbocation brings in, that is responsible for the ortho and the para products being major products, because those transition states, or the transition state leading to this sigma complex, is going to be stabilized because there is the involvement of a tertiary carbocation here. Now, you might wonder, okay, if both of them are stabilized, why do we see this difference in numbers? Why do we get 63% of the ortho product and 34% of the para product? So like approximately twice as much ortho product. This is because statistically there's more ortho positions, right? There are 2 ortho positions, whereas there's only 1 para position. So on a statistical basis, the chances of an ortho nitration would be twice as much as the chances of a para nitration. Now, this doesn't always happen. So the nitration of third butyl benzene is a good example where this statistical favor which the ortho position enjoys does not work. So if we do a nitration of third butyl benzene, again, we'll use nitric acid and sulfuric acid. In principle, there are 3 possible products: the orthonitro product, the metanitro product, and the paranitro product. Now, what we know from our previous example is that the third butyl group, being an activating group, it's going to favor ortho and para. Meta would be the minor product, like the really minor product. It's not favored here. So we have ortho and ortho. So we have ortho and para that are favored. But between the ortho and the para products, the para-nitro product here would be even more favored than the ortho. So the para product is favored over ortho product. And that's because the third butyl group is a bulky group. So in this ortho product, we have steric strain that's going to build in. And so that steric strain destabilizes the transition state that's leading to the formation of that product. The para product places the nitro group away from this bulky third butyl group. And so the para product does not have any steric strain associated with it. So the para product is overall favored in this particular case. So ortho para directing groups, which are activating groups, they favor the ortho and the para products. And among them, the para product is favored whenever sterics is a concern. Whenever the sterics becomes important, then the para product is favored over the ortho product. Ortho product is favored statistically because there are two ortho positions compared to the one para position. I hope you find the discussion useful.